Right. So in general, yeah, there could be like X's in there that you would have to substitute for.
Okay.
That's why it's necessary to like reverse engineer, solve for like X1 and X2 in terms of Y1 and Y2. Does that make sense?
Okay. Yeah.
So, right.
Okay.
No, I mean, I always forget like how the sequence of courses work in this in our math classes. Do you have to take Calc 3 to take this class? I'm trying to remember. Is that true or not?
I think the only prereq is logic,
Okay.
but I could be wrong.
So yeah. So this is a little bit of a stretch. I mean, you know, having to figure out how to do these like multiple dimensional integrals is a little bit of a stretch because you technically don't get like the full force of that until you take Calc 3. But if you take Calc 3, you somewhat explain what's going on with this like Jacobian factor thing. And I mean, partial derivatives are easy enough to understand. Basically, all it means is that you are, you know, thinking of one variable as being the variable, and the other ones you just treat like constants. Okay. There are several classes that you do that same sort of thing in, like for instance, differential equations. You learn how to take partial derivatives because it's necessary to do a couple of other things. The same thing is true here. And you just kind of accept, you accept it at face value for now. You'll get a little bit more of a robust treatment of that, hopefully in Calc 3 and maybe in linear algebra. But the explanation for what's that Jacobian factor, where is that coming from? That's something that you learn about over there in those classes. But essentially, kind of explains like what's happening. Like before you had little rectangles, and you do this transformation, like what are those rectangles turning into? What's the distortion factor that I'm paying when I do that? But essentially, it's just a generalization of what you did when you did like U substitutions and things like that. So yeah. But that thing could have lots of variables in it that you would have to plug in for potentially. Yeah. But in like the little part that's processing right now, I go through an even more specific example and that involves uniform random variables and show like what the ultimate density is. And I show that when you integrate that density, you do indeed get 1, which is at least the very least, you know, requirement that you should expect. Of course, I should still get 1 when I integrate this thing, right? And it does end up being true in the example that I do in that video that's being processed right now. So other questions? Anything else?
I was working on some of the homework problems that were related to this, and on 56, it all makes sense, but I think they actually had the answer for this one in the back of the book. When we get down to we're actually plugging in like the Jacobian, you take the absolute value of it to the -1, and then you multiply it by f of like x1, x2 times x1, x2. Is that, if that makes sense? In the answer that they have in the book, the ultimate answer is what you get for the inverse Jacobian. So I guess that means that the f of x1, x2 has to be equal to 1. How do we, like, how are we supposed to know that? Because in the previous one, in 55, they give you f of xy. They give you the joint density function. But in 56, are we supposed to, is it because they're distributed uniform variables?
Yeah, so what's the joint density of those things?
So it's just going to be 1?
Right, it's 1 whenever x and y are between 0 and 1.
Okay.
Does that make sense?
Yeah, I was making sure that I wasn't.
The Jacobian doesn't end up being, actually here, I'm actually joining this meeting here, so I'm doing two things at once. But so the Jacobian is going to have variables in a lot of these cases, right? So when you were Jacobian, were you getting variables in a lot of the cases?
Yeah.
So let me see. I'm joining our meeting here. Right. So this is the example I was working on earlier, but I'll do it. Let's just go through the first one. Is that all right? Or which one was any one of them particularly tricky, Emma?
I was just wondering if for 56, the part A, if
Okay.
it was the f of, I have my variables all mixed up here. I guess it would be x, y. If
Right.
that was going to be equal to 1.
So both y and x for this one are uniform 0, 1, right?
Mm-hmm.
So that means fx of little x is the same as fy of little x, which is just, 1 if 0 is less than x is less than 1, and 0 otherwise, right?
And then because they're independent, then
Yes,
that's just
yes.
going to be 1. Okay.
Right, because these are independent, that means that the joint density, little x, little y, is just going to be the product of these two guys, of little y, right? So what's that going to be? Well, it's going to be 1 whenever 0 is less than x or y is less than 1. So if we're on the unit square, basically, with one vertex at the origin, yeah? Okay, and it's going to be 0 otherwise. And of course, that thing integrates to 1 because it's just basically a 1 by 1 by 1 cube, right? The height is 1 on the unit square. The area of the base is 1, the height is 1. So that thing integrates to 1. That's good news, yeah? But the transformation here was, what was it? Like u equal to x plus y, and v equal to x over y. Okay. So, all right. So what's the Jacobian going to be in this particular case? So the Jacobian of x, y is going to be, well, here, I mean, like, I like to just say, okay, go to the first function. Basically, u is a function of x and y, right? That makes sense? Right, this is, I think the book called this like G1 of xy or something, right? And G2 of xy for the second thing. So you're going to take the derivative of this with respect to x. And one way you can write that is u sub x, okay? and then u sub y. And then for the next one, it's going to be v sub x and v sub y. Okay, so what is the x derivative of u? What's the x derivative?
1.
So 1.
Yeah, 1. And what's the y derivative?
Also 1.
Also 1. Okay, what is the, okay, so like v is equal to x over y, which you can think of as, 1 over y times x, right? What is the x derivative of v? What do you get?
Would just be 1 over y.
Yeah. And what about the y derivative, right? And so probably the most helpful way to think about it now is x times y to the minus 1, right? So what is the y derivative of this thing?
I got negative x divided by y squared.
Yeah, that's right. Yeah. Okay. So the Jacobian, right? You know how to do this. You're gonna go like these two things multiplied minus these two things multiplied. You get negative x over y squared minus 1 over y, right? Makes sense?
Mhm.
And so maybe I should rewrite that as so negative x over y. So I'm going to go over to the next page here. Okay. So j of xy, was it negative x over y squared minus 1 over y or something, right? And so what is this? That's like negative x minus y over y squared when you think about it, right? And I'm going to factor out the minus sign. So that's like negative x plus y over y squared. That's good because I know that x and y are always positive, correct? So I know I'm going to have to take the absolute value of this thing eventually. So when I take the absolute value of j of xy inverse, what's that going to be? Since I know x and y are both positive, basically all the absolute value is going to do is just get rid of that minus sign. Know what I'm saying? So what is this going to end up being?
So wouldn't it just be y squared divided by x plus y?
Yeah. But okay, so remind me again, wasn't u equal to x plus y?
Mm-hmm.
And wasn't v equal to, what was v equal to?
X divided by y.
Okay, so first of all, the bottom, that's just, you know what I'm saying? Isn't that just, the bottom, that's just u. And what did you get? Did you figure out what y squared was? Or how did you actually solve for these things, I guess?
I just did that at the beginning. Like I did that as my first step. So then I just
Oh,
substituted. It winds up being a lot messier if you do it my way.
okay. Well, how about this? Put u equal to x plus y. Do you see that y times v? What's y times v equal to? Isn't that x?
Mm.
Yeah? Okay, so I mean, I guess I could plug x in right there. Yeah? And so that gives us u equals yv plus y. So isn't that y times v plus 1? Yeah? So what is, what's y equal to? Isn't that right? That's good news. And incidentally, u is equal to x plus y, right? So, I mean, and that's good news for us because I can actually plug that in right there. I know what y is, which I can plug right there. So for the inverse of the Jacobian, what do we get? Well, it's going to be u over v plus 1 quantity squared divided by u. That make sense? And then I can cancel some stuff. And what am I going to get? Like u over v plus 1 squared. Do I have to worry about like u being positive necessarily? I mean, what do you think? I mean, like v plus 1 quantity, in theory, all of this should take care of itself because of what u and v were equal to in terms of x and y. But I always like to check this. You know, I already got rid of the absolute values with the x's and y's in there. Is this thing all still positive? I think so, because v plus 1 squared is positive, correct? And u is equal to x plus y, and both of those things are positive. So I think we're good to go. Know what I mean? Yeah?
Mm-hmm.
So what is this thing? F of u v of u comma v is equal to the density of X and Y with, you know, X replaced by what it is. I guess what's an X? Well, I'll just write X in here, okay? We know what X is. I could solve for X right here by taking U minus Y. But it's going to be X and then Y, whatever Y is. And then I have to multiply by this Jacobian, which is U over V plus 1 squared. Okay? But the only place where this really matters is when the density of f of sub xy is when that's equal to what? What has to be true? Okay, where do I really care about this density? When the density, the joint density of X and Y is 1? Yeah? Okay. So, I mean, look at this. Let me write this on the next slide. So I get F UV of U comma V is going to be equal to, well, it's going to be equal to, what was that? U over V plus 1 squared. And that was whenever X and Y were between 0 and 1, right? But what was Y equal to? Help me out again. What was Y equal to? Right, this was 0 less than X less than 1, 0 less than Y less than 1. But what does that translate to in terms of U and V? What's Y equal to? Didn't we come up with that?
U plus V, U over V plus 1, I think.
Was it just U over V plus 1?
I think so.
And what about X? Right, because Y is equal to U over V plus 1. U is equal to X plus Y. So that means X is equal to U minus Y, which is U minus U over V plus 1, which I guess we could simplify that. That would be U times the quantity V plus 1 minus U over V plus 1. And hey, the U's cancel, don't they? And I just get UV over V plus 1. Is that what you got for X, Emma?
Yeah.
Okay, so X is equal to that junk. So that X thing just translates to 0 less than this thing, UV over V plus 1 less than 1. Okay, and it's 0 otherwise. Okay, so that's like what the new that's what the new density is for U and V. Now there remains like a pretty, you know, like in my mind, I look at that and I say, what in the world is that describing? Yeah, I mean, look at that obnoxious thing. That's crazy. You know what I mean? Like what's going on with that? Well, I mean, one thing you could do is you can multiply through by V plus 1 and say that that just means that 0 is less than UV is less than V plus 1 and 0 is less than U is less than V plus 1. Oops, V plus 1. Okay, and you can even you could even divide by U if you wanted to in the first one to get like a range for V. But you know, you don't necessarily have to do this. So there remains a question of what that region is. Okay, but that's not what you were asked to do in this problem. What were you just simply asked to find the joint density?
Mm-hmm.
And is this the answer they gave? I'm assuming.
Yeah. Mm-hmm.
Okay. Right, and the reason it just ends up being that inverse of the Jacobian is because the density here was just 1 for these uniforms. Yeah. So, yeah. That's some like next level stuff there. Okay. So, I mean, if you haven't seen like multivariate calculus, this is the kind of thing that you embrace with vigor. So, how many of you have had Calc 3? Katie, Emma, Matthew, Elise. Have you had it? I can't see. Have you had it, Daryl?
Yes.
Okay. Well, man, this is just all trivial for you guys then. No problem. Did you do change of variables? That like general change of variables or not?
He worked through it, but he never really necessarily gave it a name.
Oh, okay. So, but you saw the Jacobian.
Yeah.
Okay. You can kind of prove the formula using, it's horrible. You know, you can use Riemann sums if you want. There's a slightly more elegant way to prove it using vector calculus. And in linear algebra, there are some pretty nice ways to actually show that this is what needs to happen. But there's a few big ones you tend to see, namely polar coordinate transformation, the spherical coordinate transformation, and the cylindrical coordinate transformation. But those are all special cases of the general situation where the Jacobian is the thing that you really need. The Jacobian in the case of the polar coordinates is R. Remember, like you have that R dr d theta. Remember that? That R is the Jacobian. And remember in the spherical coordinates, it was rho squared sine phi. Rho squared sine phi is the Jacobian of that transformation. So that's what's going on. Okay. So that's why we're doing that here. Cool. I don't know what's happening here. My thing kicked me out, or maybe I kicked it out. That's right. All right, what else? Anything else? So in that video that's processing, I worked through an example kind of like the one we just did, all right? But it's worked out in more detail. Like I actually go down to the level of, okay, why does this new thing even integrate to 1 at all? And so I kind of show why it happens to do that. Does that make sense? And it's a geometry problem. I don't even really do an integral. I just say, well, this is just geometry. The height is 1/2 everywhere. Then I need the area of the base of the thing, and I'll be able to compute what the volume is. And it's 1. Hallelujah, right? Works out. Okay. Just to prep you for what's to come, I'm going to pick and choose just a couple of topics to cover in chapter 7, because I've actually covered a fair amount of it just throughout the course. You know, talking about special things with the expectation. It just made more sense to me to talk about it back in the course in context and not separate it off as its own chapter. But there are a couple of remnant things I'm going to talk about specifically. I think that it would be worth our while to look more carefully at the hypergeometric and binomial distributions, specifically in the context of conditional expected values. And I'll show you how to write those as sums of random variables, and that will kind of lead us into what I hope we get to at the end, namely the central limit theorem. The central limit theorem is like the big bridge between probability theory and statistics. So if you go and take mathematical statistics, you'll spend a ton of time talking about the central limit theorem. That's like everything. Central limit theorem just boom, sits there right there in the middle of probability theory and statistics. It's literally the center of it all, okay? So it's a really, really big deal for sure. So I'm hoping we'll at least be able to get there and see why it's helpful and even maybe why it's true. We'll probably look at a proof that involves moment generating functions or something like that because we have a lot of experience with those. Anything else? You guys have lingering questions about anything else?
So,
Yeah, go ahead.
are you planning on adding to the homework for chapters 7 and 8?
No,
Okay.
I don't think so. Why, do you want some more problems there, Matthew?
Well, I mean, I just noticed that there weren't a lot of problems,
No.
and I ran out of them. So,
Okay. Well, there's a lot of problems there for you to just kind of work through if you want to do those. But I mean, you guys know they have like a section on more computational problems, which, I mean, you may quibble about whether they're actually computational or not. Sometimes there's problems that are more theoretical, and then there's like a self-test section, which is kind of a mixture of the two and ones that you should be able to get in theory fairly quickly. So, I mean, I would recommend going and working through some of those. Those are fairly helpful. But no, I'm not really planning on doing anything extra. But if you want to work through problems and ask me about it, that'd be great, Matthew. I like doing problems, no doubt about that. Anything else? You guys ever film yourself and think you're filming yourself, but you're not? And then every time you're not filming yourself, you actually are? You guys ever done that before? Well, I did it. It was amazing. So sorry about that. It was a fairly substantial technological snafu. But that other video should be processed here pretty soon, and then you'll have the last 15 minutes or so. Sorry about that. Apologize. So, hey, you have that quiz. Hopefully that's not too bad of a quiz. That's due tomorrow by midnight. Other than that, I don't really have anything else to say. Good to see y'all. Have a good rest of the day.
Thanks,
Yeah.
Thank you,
Dr.
Dr.
Hammond.
Hammond.
See ya.